The Sun has been exhibiting some unique behaviors lately, and it's about to undergo a significant and fascinating change: the reversal of its magnetic field. This event, which occurs roughly at the midpoint of the solar cycle, has far-reaching consequences for Earth. In fact, it's possible that soon the Sun could pose a serious threat, potentially leading to widespread chaos and disaster on our planet. To understand this process, we need to dive into the workings of the Sun's magnetic field. The field is generated by the movement of electrically charged gases within the Sun in a process known as the solar dynamo. Over time, this field becomes increasingly complex and distorted due to the Sun's rotation and convective motions. Eventually, this process leads to a complete reversal of the magnetic poles. The North Pole becomes the South Pole and vice versa. Let's break down this entire process and take a closer look at the Sun itself. The Sun is primarily composed of hydrogen and helium in a plasma state, a condition where electrons are not bound to atoms, resulting in a mixture of free electrons and ions. The Sun's interior is divided into several layers, with the core at the center, surrounded by the radiative zone and the convective zone. The core is where nuclear fusion occurs, converting hydrogen into helium and generating massive amounts of energy. Above the core lies the radiative zone, where energy moves outward through radiation. In this region, energy travels slowly, as photons are absorbed and re-emitted by the solar plasma repeatedly. The outermost layer of the Sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises toward the surface, cools and sinks back down, creating convective currents. The solar dynamo process operates primarily in the convective zone and the tachocline, a thin layer between the radiative and convective zones. The tachocline plays a key role in generating the magnetic field due to the Sun's differential rotation and shear flows. Here's something intriguing. The Sun doesn't rotate as a solid body. Different parts of the Sun rotate at different rates, with the equator spinning faster than the poles, a phenomenon known as differential rotation. This twisting and stretching of magnetic field lines intensifies the magnetic field. The solar cycle, which lasts about 11 years, involves a series of changes in the Sun's magnetic field, culminating in a reversal of polarity. This cycle is driven by the solar dynamo and includes several phases. At the beginning of the solar cycle, the Sun is in a state of solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is mostly simple and bipolar, with clear north and south magnetic poles. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the emergence of magnetic flux from the Sun's interior. These sunspots appear in pairs with opposite magnetic polarity and gradually move toward the equator. Around the midpoint of the solar cycle, the Sun reaches solar maximum, a period of peak activity, marked by the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. During solar maximum, the magnetic field becomes extremely complex and tangled due to the constant twisting and shearing by differential rotation and convection. As solar maximum wanes, the magnetic field begins to reorganize itself. The twisted and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses polarity. The north magnetic pole becomes the south magnetic pole, and vice versa. This process is facilitated by the emergence and reorganization of magnetic flux regions. After the polarity reversal, the Sun enters a period of declining activity, returning to solar minimum. The magnetic field simplifies, and the cycle is ready to begin anew. At present, we are in the solar maximum stage, and the Sun's magnetic field is on the verge of flipping. During this stage, we can expect to witness some spectacular solar activity, which could be as dangerous as it is fascinating. However, the Sun's magnetic field reversal is not a sudden flip, but rather a gradual process that unfolds as the solar cycle progresses. Scientists monitor the Sun's magnetic activity using a variety of tools and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the Sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, measure the Sun's magnetic field and track its changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots. During solar maximum, sunspots appear more frequently and are more pronounced, signaling that the magnetic field is becoming increasingly unstable and preparing to flip. While we're on the topic, let's take a closer look at sunspots. When the sun's magnetic field lines become distorted and tangled due to differential rotation, they inhibit the convective flow of hot plasma from the sun's interior. This results in cooler, darker patches known as sunspots. Sunspots aren't just interesting solar features. They can sometimes produce extremely powerful solar flares and CMEs. These phenomena release massive amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, affect power grids, and pose risks to astronauts in space. Increased solar activity can also enhance auroras but raise radiation levels in Earth's upper atmosphere. Speaking of solar flares and CMEs, while both are intense eruptions of energy from the sun, they are quite different. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They produce a lot of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as flashes of bright light and heat on the sun's surface, like a massive explosion. In contrast, CMEs are large releases of solar wind and magnetic fields from the solar corona. They can be thought of as giant bubbles of gas and magnetic fields hurled into space. When a CME occurs, it sends billions of tons of solar particles into space at incredibly high speeds. While solar flares and CMEs are related, they are not the same. A solar flare can occur independently, but sometimes a particularly powerful solar flare can be accompanied by a CME. However, a solar flare doesn't necessarily cause a CME. In terms of risk, it depends on which phenomenon we're discussing. Solar flares primarily impact communication systems and technology through radiation, while CMEs can trigger geomagnetic storms, which pose more direct threats to infrastructure like power grids. Both are part of the sun's dynamic behavior, particularly during the solar maximum phase when magnetic reversals are imminent. Solar flares can disrupt radio communications, navigation signals, and pose a significant risk to astronauts in space due to intense radiation. Coronal mass ejections, CMEs, however, have a broader impact. They can trigger geomagnetic storms that affect power grids, satellite operations, and produce beautiful auroras. CMEs also increase radiation levels in Earth's atmosphere. While solar flares are powerful and potentially harmful, CMEs are more dangerous on a larger scale because they can disturb Earth's magnetic field, threatening technology and infrastructure. During periods of heightened solar activity, the amount of cosmic radiation reaching Earth also increases, which makes satellites and spacecraft more vulnerable. Charged particles from the sun can damage electronics, disrupt communication signals, and even alter satellite orbits. In addition to technological damage, increased solar activity can impact Earth in other ways. Though the sun's magnetic field reversal doesn't directly influence Earth's climate, changes in solar activity might have some effect. For instance, increased solar activity could slightly warm Earth's atmosphere, potentially worsening current climate change trends. One of the few positive effects of heightened solar activity is the enhancement of auroras, the stunning light displays known as the northern and southern lights. These occur when charged solar particles interact with Earth's magnetic field and atmosphere. Though auroras are often associated with the north, they can also be seen near the South Pole. During periods of high solar activity, auroras become more frequent and visible at lower latitudes, offering spectacular nighttime shows. Despite the beauty of auroras, the sun's magnetic reversal could bring chaos if we are not prepared. One major risk is the increased likelihood of geomagnetic storms. These storms happen when solar wind, filled with charged particles, interacts with Earth's magnetic field. In extreme cases, geomagnetic storms can cause widespread blackouts and damage infrastructure. A historical example is the Carrington event, which occurred on the morning of September 1, 1859. British astronomer Richard Carrington observed the sun through his telescope and witnessed a brilliant flash of white light from a group of sunspots, marking the first recorded solar storm. This flare released a massive CME, which reached Earth in just 17.6 hours. An incredibly fast journey given the 93 million miles between the Sun and Earth. When the CME hit Earth's magnetosphere, it triggered a geomagnetic storm of immense intensity. The impact was immediate and far-reaching, disrupting Earth's magnetic field and causing currents in the ground and telegraph lines. Telegraph systems, the backbone of global communication at the time, experienced severe disruptions. Sparks flew from telegraph machines, operators were shocked, and some stations even caught fire. In some cases, the induced currents were so strong that operators could send and receive messages without the telegraph batteries. One of the most striking results of the Carrington event was the vivid display of auroras. During this storm, the auroras were so bright and widespread that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing vibrant colors lighting up the sky. The auroras were so intense that they illuminated the night sky to the point where people in the northeastern United States could read newspapers by their light. In the Rocky Mountains, gold miners mistook the brightness for daylight and began preparing breakfast. Now imagine if a solar storm of Carrington's magnitude were to hit Earth today. The consequences would be catastrophic. The Sun is currently undergoing a critical transformation, the reversal of its magnetic field, a process that occurs roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, can have significant consequences for Earth, potentially causing widespread disruption and disaster. The Sun's magnetic field is generated by the movement of electrically charged gases in its interior, resulting in a complex magnetic field that periodically flips its polarity. The Sun is primarily composed of hydrogen and helium plasma, with energy generated by nuclear fusion at its core. This energy is transported outward through the radiative zone and then by convection in the outer layers. The solar dynamo, which operates in the convective zone and the tachocline, produces the Sun's magnetic field. Currently, the Sun is in the solar maximum phase, where sunspots and solar activity are at their peak, leading to potential dangers such as solar flares and CMEs that can disrupt satellite communications, power grids, and pose risks to astronauts. Scientists monitor the Sun's magnetic activity and sunspot behavior to predict the timing of the magnetic field reversal. Sunspots, which result from twisted magnetic lines, can generate solar flares and CMEs. Solar flares release radiation, while CMEs release large amounts of solar particles into space. While these phenomena can enhance auroras, they also pose serious threats to Earth's technology and infrastructure.